All right. Thank you for being here. Happy Thursday. A few reminders for you. So first reminder is the project that's been assigned. And so I know things are busy right now with midterms and everything, but you should start to choose your groups and brainstorm what kind of topic you want to cover. Again, this is really open-ended. So what you're required to do is by the end of next week, schedule a time to meet with me, and that will help me to finalize your group and help talk you through what topic you're going to choose. So that's due by the end of next week. I'm just reminding you now. For video 2, the algorithms video, I've set the due date. I'm making it due after spring break, so the Friday after the break, so that you have time to work on it the week when we come back. And I've decided the groups for you. So I'm gonna pause recording and pull that up. Okay, I don't think I'm gonna talk too much about the assignment because it's pretty much the same as last time. I am going to, let's see, some of the things I saw as I was grading were like you didn't submit your code with the video, and so I took down points for that. Or you didn't submit the feedback form, and so I took off points for that. So everybody has to make sure to fill out the feedback form, and that's where you get your collaboration grade. I took points off generally if you didn't like draw examples, which is kind of what I'm looking for. But again, I was a little bit vague about that. So let me know if you have questions in how that was graded. Hopefully I'm going to be more clear in the specifications for the next one. So as always, take a look at it and then let me know if you need any clarification or if you've got questions, and I'm happy to talk you through it. If you're confused about what your role assignment means, I'm happy to give you an example and help walk you through that as well. And the goal of the videos are not only for you to understand what's happening in the algorithm, and like for the programmer to like implement it. Like we're computer scientists, we know that programming is an important skill, but so is presentation. Because if you like go into coding interviews, or if you're working with a manager who doesn't really know maybe the day-to-day programming stuff that you do, being able to explain the things that you write and explain what work you're doing at a high level with some simple examples is a really useful skill. And being able to pick and choose what sort of information is important for the sake of clarity is also important. And so that's the goal that the videos are trying to accomplish, to not only help you to understand the algorithms, but also have practice at presenting and making those kind of decisions to, convey the information in a clear way. That's what we're trying to do here. Okay, so last time we covered BFS. Today we're going to do DFS and hopefully those 3 other algorithms. I'm guessing we're not going to get to the packet problems today. So that's for after spring break to warm our brains back up to algorithms. Okay, so to remind you where we've been looking at graphs, which is, do I have, nope, it's not immediately there. So graphs are, you need a packet? I'll hand it out in a second. So graphs are collections of vertices or nodes and edges, which connect the two. And we're looking at going through that graph. And how can we, for traversal, we're looking at how can we go through all the vertices. And so we looked at breadth first search, which involves, there it is, where we start somewhere and the main data structure is a queue where we're going to add something to the queue and then add its neighbors. And then dequeue, add that thing's neighbors, and so on. So we looked at these examples, and the complexity of that is O of V comma E, because we're processing, at the worst case, we're processing every vertex and every edge. So just add those two together, and that's our complexity. We talked about the sort of applications for that. And then we've got DFS, which is, so breadth first search, as you can imagine, favors broadness over depth. So in depth first search, we're going to, instead of looking at all of, remember here, instead of looking at all of the children, first we're going to choose one and take a deep dive down there. And then we'll go back up. And then we're going to choose the next child, go down the line to all of its children, and then go back up, and so on. So that's the idea. We're going to focus on the children before the neighbors. So again, we're going to watch the video, and then we'll do examples. I think, is that the wrong link? That is the wrong link. Thankfully, the other one is here. Okay, let me fix this. All right, so let's just walk through DFS for the first one, and then I'll okay, let's see. There it is. Okay, so with DFS, with BFS, we're working with a queue. With DFS, we're working with a stack. So let's assume maybe that we start at A. So I'll have my stack here. And so first I'll push A. And then once I've processed it, then I pop it. When you pop it, I would like you to write the order in which you pop it. So like A gets written first. And then we add its children, so B and D. I could put B first, or I could put D first. Well, maybe you put D first so that, yeah. Yes, you were right. Okay, so maybe it's not in particular order. Yeah, for some reason this edge was invisible to me. Okay, so we push all of its children, and we're done with A. Next, we look at the first thing up in the stack, which is E. So we pop it, we write E, and then we add its children who aren't in the stack or haven't been processed already. So that's, yeah, so I pushed D, B, and E. And I could have written them down in like E, D, B, or B, D, E, or something like that. That order is up to you. Okay, so looking at E, we've got two who we haven't put in the stack yet, C and F. And so now we look at what's up next in the stack. So in breadth first search, we would go back to B and D and process those, but we're not doing that in depth first search. So next up is C. And then out of all the neighbors, we've already got all of them either over here or in the stack. So there's nothing else to add. And that's the case for all the rest of them as well. So C is done. Then F is also done. B, we've got all of its neighbors. And then D as well. So instead of using a queue, we use a stack, and we just go by what's on top of the stack. Okay, so take a few minutes, talk with your neighbors, and work through at least the first two on the, on the packet. The other two on the first page.
Well, children are B, C, D. Starting so all of sorry. I mean, well, they're all still as children, but we only
Yeah. Things need to know, but you have to go with.
Yeah,
If you are at a,
I mean, whatever order.
remember we also got.
Yeah.
And so get the.
I mean, you'll get a different list, it doesn't matter.
So the way.
Like you look at it.
Yeah.
So that once you find there's like, it's very mind blowing, yeah. You can say, okay, and still one, still one, right? Oh, start with C. What did you do? He doesn't have any children. I just started. Yeah. I mean, I got a different order. It just makes you put them in your stack. For the purposes of this exercise, I don't think. That's not good. Yeah. That's just whichever one you want to start from. You just have to do it. Each have.
Let me pause and get the attendance that I missed. Okay, so let's maybe look through this second one. If you've got this, then maybe you want to keep working on it. The other ones that you were doing. But let's look at the case where we start from H, and I'm also going to draw the DFS tree as we go. So we start from H. So we push it and then pop it, and then we push its two children, F and G. So here's the time where I make a decision of in what order do I want to push it. In the video, they did it in reverse. They pushed in reverse alphabetical order. So that way the thing earlier in the alphabet is on top. So like that's the difference between F on top and G below, or G below, or F below and G on top. So this is the order in which we push things to the stack, that we make a decision. So I don't know, maybe let's push G first and then F. But as we go, we've decided that the edge from H to F and the edge from H to G, those are in our DFS tree. Okay, so now F is on the top of the stack. So we pop it. And then we look at its children. The only one we haven't included so far is E. Okay, so now we look at E. And we add its children, which are A, C, and D. Again, we have choices for how we want to push these onto the stack. So if I do D, C, and then A, now A is on top, and we do the process again. So write A, we add its children, which is only B left. And then we'll pop B. It's got no children that we haven't already seen. And then we've gone through all of the vertices, so we've seen all of the other ones. So we just pop it off as we write down. So C, and then D, and then G. So again, if you started with H, it should look roughly like this, although this half of the graph might look a little bit different depending on the order in which you pushed the elements. So this is what my depth first search tree looks like. Yours may look a little bit different. But as long as you still follow the rules of the algorithm, then you're good. Okay, is there any other examples that you want us to go through? The last one on this one? Yeah, so remember for BFS how we said when you run out of something, then you restart? It's the same thing. Yeah. So you choose another one, maybe you say alphabetical order wins. And so if you start from A, then it probably looks like this. And then maybe you say, okay, now start from E and do the same thing. Okay, other questions? All right, let's keep going. I'm not a big fan of the book pseudocode, but I have it here in case. I don't think this is oriented well. There we go. Now we can see the whole thing. Yeah, I think the book pseudocode is a little bit just more, it's more complicated than the intuitive version. It's just adding another level of detail as we want to be more precise about it. Okay, we did that. In terms of applications, one of the applications of DFS is topological sorting. So let's say we're working with a directed acyclic graph. So directed, remember, meaning that there are arrows. So like the first graph on the second page, that's directed because it's got arrows. And acyclic just meaning there are no cycles. Cycles being something that go, like you can start from one and go around and get back to the other. So even though in this graph that it looks like there's something that are cycles, like there's a triangle here, but if you follow the arrows, it's not actually possible to start from one place and go around and get back to where you started. So there are, in fact, no cycles in this graph. And you can use DFS to find this topological sort, which is when ordering the nodes so that every edge is going to go from left to right. So you can use DFS, like if you start from G, then you can go on and order the graph so that it looks like this. Okay, so that's kind of topological sort. If your group wants to do this for your video, you could. Okay, so let's talk about weighted graphs. Remember at the very beginning of the semester, we kind of talked about this, where the edge weight could mean anything. It could mean like how long the drive is, or how much time it's going to take to go somewhere, or how much it's going to cost, something like that. It can mean whatever we want. But the two main types of problems that we'll look at for weighted graphs are one is a minimum spanning tree, which is where we'll maybe start at a vertex and then find where. So we were coming up with a spanning tree in DFS and BFS. But now when we look at with weights, we want to find what's the spanning tree that has minimum cost. So like there are choices of edges that we could choose to include. What's the choice that gives us the lowest total cost? And then there's shortest path with Dijkstra's algorithm, where if we started a vertex, we want to know what's the shortest path tree. So like if we start at one point, what's the shortest or minimum cost path from this node to every other node in the graph? So it's still a tree, but it's has slightly different purposes. The basic ideas with both of these categories of problems is we're looking at greedy algorithms. And so if you think of greedy, like if a kid wants all of the cookies and candy, we're trying to take the opposite approach, where we are maybe stingy, where we don't want the highest cost. We want the lowest cost possible. We're like going to the store with all of our coupons clipped and everything. So in these, we don't necessarily care if there's a lower cost later down the line. We care if there's a lower cost available right now. So that's where the smallest option available comes in. Okay, so we'll talk about prims. So I won't go through the video for this one. We'll do it for Dijkstra, but I think for prims and Kruskals, we'll do the examples instead and demonstrate it that way. The basic idea with prims is we're going to start somewhere. And then we look at all the available edges that we have and ask which one is cheapest. Then we choose that. And then we repeat. We look at all available edges and ask which is cheapest. Choose that one, repeat. And so we choose the cheapest edge as long as choosing that one, as long as going to the next vertex isn't going to introduce a cycle. So a cycle being start somewhere and we are able to go back around to it. So as long as we can't, as long as the edge won't do that, then we're good. Yeah.
So for an adjacency matrix, is that the same thing as when we're doing the whole in the class for finite automata? Is that the same things that we do instead of the weights, it's the characters for the language?
Let me scroll back up to that slide. I'm not familiar with how that class was taught. This is what so the left thing, this is what I'm talking about for adjacency matrix. And this is adjacency list, which is, so like the rows here are the vertex numbers. This array is the vertex numbers. And then for this one, we've got a linked list of here are all the vertices that number 1 is adjacent to. And then here, there's a 1 in a column if that vertex is adjacent to another one. Okay, so here's the complexities for those. For this one, it depends on how you are storing the graph. So adjacency matrix is v squared. Depending on how you store the vertices and edges, it can vary. So when you make your video, if you're making it on Prims, you have to explain, here's how I stored the graph. Here's what data structure I used. And as a result, here's the complexity of these operations. So when you make a choice, then you have to explain the complexity of what that means. Okay, let's look. Whoop. All right, so this is the version that has weights on it. I took a random number generator and went 1 to 100. And so we're going to do Prim's algorithm here. So we have to start somewhere. Maybe let's start at A. And as I go, I'll draw the shortest path tree over on the left. So we look at all the edges that are available from A. That's weight 18, weight 50, and weight 21. Which one wins? 18. That's the smallest. So we draw the edge from A to B, and we've got weight 18. Now we've got options 21, 50, or B's got a new edge, 47. 21, 50, or 47. Which one wins? 21. So we draw the edge from A to D. Now we've got 50, 71, or 47. 50, 71, or 47. 47, right? Here, actually, let me, I feel like this is easier when we draw over it. Okay, so now it's kind of easier to see, here's the edges available. So either we go 47, or we go 50, or we go 71. And so then 47 wins here. So now we've got either 50 or 16 or 71. 16 wins. So from C to E16. Now we've got an option of 73 or 68. We cannot choose 50 anymore. We cannot choose 71 anymore. Because if we chose 50, that would make a cycle in our tree. Do you see that? Where like if we drew this edge from A to E, then we could go from A, B, C, E, and then back to A. And that's not allowed for our tree definitions. So as we go, now 50 is disallowed. And for the same reason, 71 is also disallowed. So we only really have two options, 68 or 73. And in that case, 68 wins. So it ends up that our minimum spanning tree ends up being what we call a path, which is just, we could move it around and write it just in a straight line. But it's still a tree. There's no cycles. So great. Then we can pull up a calculator and add it all up. So 21 plus 18 plus 47 plus 16 plus 68 equals a cost of 170, which gives us a minimum spanning tree. Okay, that's Prim's. Take a second and run through that with the other graphs as well. So try that algorithm again with the others. I recommend if you've got colored pens or pencils, pull those out, or maybe highlighters. I think colors are useful because we're also going to be using these graphs for the other two algorithms as well. So keep that in mind. Let's come back. I will just note that if you are working on this one, the complicated one, whichever one the node you start with greatly determines the shape of the tree. Where if you start with 1, then you have pretty much an easy job of it. But if you start with, I think someone started with 4, was it? Like if you start with 4, then you run into a wall and then you have to restart and then you have to restart and so on. So depending on where you start, you will get either a minimum spanning tree or a minimum spanning forest, where forest is like a set of trees, which this gives you a forest because the graphs are disconnected. But yeah, so it depends where you start. Any questions before we go forward? Okay, I just want to clarify. So for these, I'm looking for this information of what's the spanning tree and what's the total cost. Okay, let's look at another one. So another minimum spanning tree. So we're going to get the same kind of result of here's the tree and here's the cost. And this is Kruskal's algorithm. And it works fairly similarly, except instead of choosing vertices like we did, where we start with a vertex with prims, and then we add a vertex based on the smallest cost. Instead, here, we just look at edges. So we just choose the smallest weighted edge across the whole graph. and build it up that way. Again, as long as choosing that edge isn't going to create a cycle. So let's look at the example. So I'm going to do this. I'm going to erase the drawings that I've done here. If you would like a new version, I still have versions of the packet. Okay. Okay, and let's maybe, okay, so this, in Kruskal's, I'm not going to choose a vertex to start with, because that's not how the algorithm works. Instead, I look at all the edges available, and I just choose the smallest. So out of all of these edges, which weight is smallest? 1, D to E. So I choose that edge. And as I'm choosing that edge, so too do I get its vertices. So now what's the next smallest edge in this graph? BC? 47? Oh, EC. EC, 16. Yes. No, wait. 16. Next is 21. No. Is the next one 21? I probably erased it when doing the, yeah, I think I erased it when I was erasing the other drawings. Okay, let's start over. And trying to be careful not to erase any of the other weights this time. Okay, now, what's the smallest edge? 16, yes. So E and C of weight 16. Now what's the smallest edge? 80? Wait, 18? 80? Oh, A to D. A to D. A to B. That's not distributed well, but that's fine. It's a graph, doesn't matter. So yeah, so I'm not, so with prims, I start somewhere and I build the tree up. Here, I'm just kind of choosing of the available options. And then we hope we get something connected at the end. What's the next smallest edge? 21. What's the next smallest edge? 47. So now we're connected. Hooray. What's the next smallest edge? 68. So yeah, so that's the next one that we're actually going to take. The next smallest edge is 50, but because it creates a cycle, so if we added this A to E, that would be a cycle, and that's not allowed. So 50 is now disallowed. So yeah, so 68 ends up being the next option. So 68 E to F. Now we'll erase this dotted line. And then we've got all our vertices. So, and then, so this would, if there were more edges, this could continue, but all the remaining edges would create a cycle. So we're done. So the cost of this one, first of all, is it different? 1847, 1668. So in this case, it's the same thing as what Prim's gave us, but it's a different process to get there. So this was what, 170? Okay, so try using Kruskal's algorithm and see if it gives you this same result, or does it give you something different? Go for it. So choose the smallest edge every time. All right, let's come back. All right, can someone tell me what the cost for the minimum spanning tree they got for this one with Kruskals? 138. Did anybody get cheaper? Is it the same one as Prim's? Okay, cool. What about this one? What cost did you get? 172? Is it the same one? What about this one? What cost did you get for this one? Adding things up. Yeah, 298. Anybody get better? Is it the same one that you got for Prims? Okay, so it doesn't always give us the same results. That's good to know. Let me know if you got something less than 298. What about the last one? Did anybody get cost for this one? If we didn't get there, that's fine. Or yeah,
That's the.
144. Okay. Anybody else get something cheaper? All right, fair enough. One of the things that I want to talk about is how you implement it. Someone over here mentioned that if you just like sort all the edges, then it's easy to just pick this one as long as it doesn't create a cycle. So if you're assigned Kruskal for the video, that's the strategy that I recommend. Okay, we did that. All right, we've got like 15 minutes left. So maybe let's watch the Dijkstra video and do an example, and then maybe we'll come back later and finish through it. Because Dijkstra is a little bit maybe more involved. It's got the same kind of idea. For this one, if you have a pencil, I recommend using a pencil. I'm a kind of person who like wants to do things in pen. But for Dijkstra's, I really, really recommend pencil because there's a lot of erasing a number and then redoing it. Okay, so let's watch this one.
Today, I'm going to teach you how to.
Let's pause recording. So the idea for Dijkstra is we're still working with our graph. So let's erase that. Nope. Was that a 16? Or was it 16? So we're going to have an unvisited list. A, B, C, D, E, and F. And we're also going to have a table. So maybe you write it all down one big line, but I'll split it into two so we can more easily scroll up and down. And so we choose a point at which to start. So let's choose A. So the distance from A to A is 0 because we're already there. And initially, every other distance is infinity. We haven't looked at anything yet. Now we look at the vertices that are reachable from A. So kind of like prims, right? So we look at where can we go from A? And so we see, here are the options. We can go to B for 18. So B is now 18. This is why I recommend like a pencil and eraser. We can go to D for 21. Sorry, that's supposed to be an infinity. Or we can go to E for 50. That's supposed to be a 5. Okay, so now we've gotten all the vertices that are reachable from A. So we cross A off the list. Now we look through our distances list. Which one is the smallest? It's B for 18, right? So let's look at B. So from B, now we can reach C. So for 47, and can we do any updates? So I think the answer is no. So there's no way to update any other value because we can only get to C from B. So I think B is done. Cross it off the list. Now we look at the rest of the things that we know. We've done A, we've done B, so now it's C, D, or E. Which one's smallest? D. So let's look at D. From D, we can reach E. And so we could go from D to E for a cost of 21 plus 71, which is 92. Is 92 better than our current listed time of 50? No. So we don't change anything. And I think that's all we can do for that one too. So we calculate here's another cost. Is it cheaper? No, so we don't do anything. So D is now done. So now we've got a choice of C or E. 47 wins. So we look at C. So currently we're going from A to B, A to D, A to E, and B to C. Wait. Hold on. Wait, I made a mistake. I shouldn't have written down 47 for C. Yes, you add 18 plus 47. 18 plus 47 is 65. Okay, so now when we're looking at between C or E, or technically F, now we have to choose E because E is the smallest. So we choose E. Now we can reach C from E. So we have to ask, is 50 plus 16 less than 18 plus 47? And I think the answer is no, just by 1. I think this route is 65, and I think this route is 66. Yeah. So because this route going through E to get to C is more expensive, we disregard it. Now we can reach F though, so that's good news. So if we go to F through E, that's 50 plus 68, which is 118. Could have done that in my head. So we can reach F through E. Are we done with E? I think so. Okay, now C versus F. 65 versus 118. 65 wins. So we look at C and we ask, could we get to E cheaper? 18 plus 47 plus 16 versus 50? No. Could we get to F cheaper for 18 plus 47 plus 73 versus 50 plus 68? I think the answer is also no. So I think we're done with C. And then F. We look at if is it cheaper to go from 50, 68, 73 versus the current cost to get to C, which is 65. That answer is clearly no. So I think we're done. Okay, so we've got 3 minutes. So maybe very briefly, try and do this one, maybe this one and the disconnected one. See if you can get through these. Yeah, so do as much of this as you can. On Tuesday, we might look at this a little bit, but we're gonna review for the exam on Tuesday. And then the exam in question is next Thursday. So that's our plan going forward. We'll pick up with the graph algorithms and stuff after the break. Question? Not yet. It will be. As soon as I finish writing the exam. Okay, go for it. Try this out. Let me know what your questions are.